All right, so today we're talking about 3D shapes, okay? A lot of what we do is going to be analogous to what we did in 2 dimensions. Today I'm just going to introduce a lot of vocabulary and some wording we're going to be using. So to start, what we've got is, a polyhedron, analogous to a polygon. A polygon in 2 dimensions is something that is closed, 2-dimensional, and made of straight line segments. So you attach a bunch of toothpicks together end to end, and you make a polygon. Now in 3D, it's the same thing. We have a closed 3D solid. So there's an inside and outside. You could put some water in it and close it. And then it's made of 2D polygons. So there's no curves. You have all these things. These are made of triangles and rectangles all attached end to end and sewn or glued together. And there's an inside and there's an outside. Now, the ones on the right aren't polyhedrons because they have curves. Anything to do with a circle or an arc or a curve, it's not technically a polyhedron, but you could think of it as having infinite sides, and we'll talk about that more as we get into cylinders and cones. Okay, and just the wording you see here, polyhedra, is the correct plural of polyhedron. Often I'll just say polyhedron, so either one. Okay, a couple words to talk about. We have faces. Instead of saying sides, although very often I will slip and I will say the sides of a cube, but correctly, the polygons that make up a 3D shape are actually called the faces. It's like, in the English language, when we talk about an argument, a lot of times we'll say, oh, that's like, I'm looking at a different facet, like face with a T at the end. I'm looking at a different facet of that. That's analogous to this, where we've got different faces if you look at the 3D shape from a different angle. So the face here is this top rectangle, the top of the shoebox here. That's one face. And then the side of the box here would be another face. Okay, I'll delete that. So there's one face on top. Now the edge is, let's do it in yellow. The edge is this 2-dimensional line right here, where two faces meet, two polygons meet at that line segment. That's an edge. And then finally we have a vertex. A vertex is just a corner, right? So the vertexes of this would be here, here, here. So we have 8 vertices total because we'd have 4 on the top face and 4 on the bottom face. Okay. Now, basically all of the 3D shapes, not every single one, but the vast majority, will either be prisms or pyramids. These are going to be the vast wealth of problems that we look at, whether we're talking about surface area, volume, the cross-section of a shape, identifying with vocabulary. These are going to be the 2 most common. So a prism is essentially, you have any shape you want. You take any polygon. Let's say I make a star. Ooh, this is not turning out well. Let's say I make a star polygon. Now, if I were to take that star and just copy it and paste it over here, I could, let's erase that line there. So I could then connect it and say this is 3-dimensional. I now am projecting this star into space. This star is getting projected backwards. So it's like a stack of star-shaped Post-it notes, where if I take any individual slice, and these would be behind is why I'm doing it dashed. So I can project this star into space. It's like a bunch of cross-sectional slices of stars, a stack of 100 star Post-it notes. So if I look straight at it, straight at the base, all I see is the star. But as I rotate it to the side like this, I can see that you have these stars stacked, right? And then another star stacked here. And then, whoa, that was a bad drawing. Okay. But the idea being is that it's one shape projected into space. The definition here I wanted to highlight is 2 bases, and they are congruent. They're parallel, so like 2 sheets of paper and a stack of paper are flat. They won't intersect if we projected them off in all directions, right? If they're, page 1 of a book and page 100 of a book, will lay flat. They're oriented the same way in space, but they'll never touch each other, even if the pages were, the size of the classroom. And then they're connected by parallel lines. So in other words, looking at these images here, I have, let's do bright pink here, I have a triangular base, and then I have another triangular base in the back, and I connect them with 1, 2, 3 straight lines. In this one, I have a square or rectangular base. I have another copy of that in the back, and then I connect them with 1, 2, 3, 4 straight lines that are all parallel to one another, and so we would get a copy of that back. Over here, we would have a pentagon as the base being projected backwards. Again, I'd have another copy of the same pentagon in the back, and then I'd connect 1, 2, 3, 4, 5 corners back with parallel lines. And you can do this with any polygon. You could even do this with circles and make cylinders like soda cans. You could do this with any shape you want, project it into space, and it's analogous to a prism. But if it's a polygon with straight edges, it is a prism. Now, a pyramid is very similar in that we're projecting something through space, but what's different here is once we have this base, rather than keeping it the same size, we shrink it down to a point. So this is like a stack of Post-it notes where they're getting smaller and smaller and smaller. If I cut through this at any point, I'm going to erase those lines. If I cut through this at any point, I do get another square or rectangle getting smaller. Here I would get another rectangle getting smaller. Here I would get another rectangle getting smaller. So it's like we did with dilations, except now you're dilating in 3D. So every cross section you take will be the same shape as the original. If I cut it this far from the base, I get a hexagon, right? As long as I'm parallel to the base. If I cut it up here, I still get a hexagon. It's just smaller. But every cross section you take in a pyramid is exactly the same shape as the bottom. It's just smaller. And so you get this ever shrinking version of the bottom shape, getting smaller and smaller and smaller till it's a point. Now, a real easy way to think about it is it's one base, and then you connect it all. Rather than connecting it to a point, you connect it all to the vertex, or all the vertices of the base to a single point. So you take every single vertex of the base and you connect every single one of those up to a single point and collapse it down, and that makes a pyramid. Okay, now the naming of these, all we say is what's the name of the base, and then is it a pyramid or a prism? So this is a rectangular pyramid, hexagonal pyramid, heptagonal pyramid, the 7 sides. Over here we have a I'll write it. We have a triangular prism. Here we have a pentagonal prism, and each one of those and so on and so forth. Hexagonal prism, octagonal prism, decagonal prism. And one last thing about those is they don't have to be sitting perfectly upright, okay? A right prism is perpendicular to the ground, or orthogonal in 3D, but you can think of it like perpendicular to the floor. It doesn't have to be that way. I could take my Post-it notes and shuffle them off to the side a little. It'll still have the same height. It'll still actually have the same volume, which is cool. This is analogous to having a triangle that has a certain base and height. And then looking at another triangle with the same base, whose top point I moved over, but it still has the same height. Those have the same areas, the same thing as this. So it'll have the same volume, but what we're doing is we're sliding the tip over so this stack is no longer at a right angle with the table. The difference is we just call it a right prism, which we'll deal with probably more. And then we have an oblique prism. Same thing with a pyramid. If the top of the pyramid is directly over the center, right angle straight up, then we say that is, you know what? That is a right pyramid, this one being a rectangular pyramid. But if the top is not above the center, it's above some other point, we call it oblique. And that point could be outside, right? I could make a rectangular base and have it connect to this over here. So I could have a very oblique pyramid, and that's okay. All right. So we're not going to use these that much, but this is something that's interesting. So a regular polyhedron has to, the word regular meaning all sides, faces, angles, vertices, everything has to be the same. Rotational symmetry has to be there. Every measurement has to be the same. So it can't just be that it has all of the faces being the same, because on that face, one edge might be longer than another. So what it has to have is it has to have congruent regular polygons. So not only are each of the faces the same, but the faces themselves are regular polygons. And Plato, the Greek philosopher, studied these, proved a bunch of things about these. So these are called the Platonic solids. And there's actually only 5 regular polyhedrons, and they're shown here. You are very familiar with a cube, I am sure. The other ones might be newer to you, but these are just the only regular polyhedron called the Platonic solids. We're not going to use those that much, but that is interesting. You found that around 400 BC. Okay. Concave and convex, I didn't go into detail here. We explored this a lot with 2 dimensions. It's analogous to 2D. Essentially, does it have an indent, right? There are geometrical definitions like does one edge extend into the interior of the 3D shape or along a face of the 3D shape? If it does, then just like this, it's got a little cave or an indent. So that cave or an indent makes this concave. Whereas if every single vertex is pointing out of the shape and there's none pointed in, then we say this thing is convex. Okay. So I want to really quickly go over how to draw a prism. It doesn't matter what base shape there is. If you want to draw a prism, a really easy way is you start with 2 copies of the shape. Now, already drawn here is a rectangular prism. Let's say off to the side, I'm going to draw a triangular one. So I'll draw 2 triangles. I want the exact same triangle. They don't have to overlap. They can be anywhere. In general, though, I wouldn't put them horizontal or vertical from one another, because then when you connect sides, it overlaps and you can't really tell what's going on there. So having them be offset vertical and horizontal, so you have it diagonal, that makes it easier to draw. So anyways, I drew 2 copies. Then down here, I'll take those 2, and now you know what? I'm going to connect, so let's copy that and paste it down here. Whoa, that's cool. Okay. So now the next one is let's connect all the vertices, okay, with parallel lines. So I'm going to connect here to here, here to here, and here to here. So bottom left connected to bottom left, top to top, right to right. And the last one is now you got to decide which part's in front, because the stuff that's behind, like imagine this was solid painted black, you can't see through it. What parts of the shape are you actually seeing with your eye, and what part are you imagining is behind the building, behind the thing? And so I would realize that, like, oh, I'll just switch to white here and make mine a little thicker, and I'll say, you know what, I gotta make this one dashed because this one was behind the shape. And if I'm looking at the top here, also this one here is dashed and this one here is dashed. And so now I realize that just going over this with orange, I realize that I can see the front of my shape and I can see this one side here. But the other parts are behind the shape, so I can't see them, so I make those dashed. And I showed here with a rectangular prism also. Okay, that's just a quick how-to. Something to remember is just that there's really only 3 directions that you draw in. Unless, I mean, you have a pentagon or hexagon. But if you have a rectangular one, it's either up and down, it's left and right, and then there's diagonal. Or it's just draw your base, and whatever your base is, then everything goes in the connect to diagonal direction. Okay? So the last thing I want to mention is cross sections. So a cross section is cutting something and seeing what's inside, right? If you use a really sharp knife or laser to cut through a watermelon, then you open up and you're like, whoa, look at that red fleshy inside, some black seeds, some, there's a white rind around it. But the idea being, if I took a sword or a laser and cut straight into here, parallel to the base, it kind of looks like, if I draw it, it's like kind of looks like this. And I'm like, I don't know, is that a parallelogram or something? But you got to think in 3 dimensions. If you're looking straight down at this and you cut it and you take the top off, this is actually a rectangle. Okay, similar over here, imagine I use this plane to slice through that soda can. I would get this in 3D, or in 2D, what it would look like from the top is a circle. Now I could have cut it diagonally, and here's another drawing. See if I cut it diagonally, and this is a hard way to think about it, but in one dimension, this dimension, it's just the width. right? So the width stayed the same whether it's slanted up and down or not. But what happens is, because now instead of going directly across, we're making it a longer path to go up and down. Instead, now this circle becomes an ellipse because one dimension of it starts to get stretched. And this is where cross sections get really cool. A challenging problem, and I actually have it on the board right now, although you can't see that, is to actually use just a cube. So every side the same, angle the same as a regular polyhedron. Use a cube and cut it with a cross section, and you can do so many shapes by just cutting a cube. Start with a triangle, right? You go, okay, well, I can make a triangle if I take my cube and I just slice with a thing and I just slice off this corner right here. There's a triangle. I just take off a corner, that's a triangle. And it's like, well, how could you make a square? Well, okay, a square would be if I cut straight down, right? Cut the cube in half. And it's like, well, how could you make a rectangle? And you say, oh, shoot, that's starting to get harder. And what that would be is just moving this closer to one side. So now you get, if I draw it again, here's my cube, and you get, okay, well, if I cut it from here and then diagonal, now this is just the width of the cube. Let's say it's a 1 by 1 by 1 cube. This is 1, but now this would be like, you have to use some trig or something. Maybe it's a square root of 3 if I pick the right angle, but it's longer. So you would get a rectangle, and you can cut it into a, let's see, isosceles triangle, equilateral triangle, scalene triangle, pentagon, hexagon, trapezoid. There's so many things just from a cube and just with a single plane. So a problem like that is really cool. I have that written on my board right now. You might want to just explore and see how many shapes you could make just by cutting a cube. Okay, so I'm just going to do some homework problems. The bell's going to ring in about 15 seconds. We'll just ignore that noise. So the first one is determine whether it's a polyhedron. So right away I can say, yes, made of straight lines. Yes, made of straight lines. And no, made of curves. Okay. Now the next says, write the name if it is a polyhedron, and then explain your reasoning. So each one's going to come in a first and a second, where the first one describes it, and the second one is either prism or pyramid. So right away, the first one, I can see that this is the base, and then every side of this base, or every vertex, is connected up to a single point. So here's my base at the bottom, and then connected up to a single point. So this would be a pyramid for sure. And then the question is, what type of base is it? And this is just a two-dimensional polygon. So 1, 2, 3, 4, 5 sides. So this is a pentagon. And then just like instead of saying, I hit the ball soft, you'd say I hit the ball softly. Instead of saying, you know, something, well, you would say something is blue, but you could also say something's blue-ish. So same kind of thing, we'll say this is pentagon-ul. And just uniformly, you can add that AL at the end. If you say pentagon pyramid, that's totally okay. But correctly, pentagonal pyramid is becomes an adjective, an adjective describing the pyramid. Now, this one over here, I can see, okay, there's a base on the bottom. Okay, this is the base. And then look, it's going up to another of the same base. So here's my base. There's two copies of it getting projected between. So this is a prism. And then what is the base? I count the number of sides and I say, ooh, that's a hexagon. And I'm going to add that ul. So hexagonal prism. This other one isn't, so you can't technically call it one of these, but it's like a prism, right? And the way you would find the volume of this when we get to composite shapes is, you would say, well, it is just a shape projected back to the same shape, right? So we could still find the volume of it the same way. All right, so scrolling down, let's look. Describe and correct the error in this, okay? So this isn't, if we look at the base as being that bottom shape, it's not a pyramid that connects like this. It's not a prism that would go to the same shape at the top. And the big misconception with this is that people always assume that the bottom thing is the base. And the base does not have to be on the bottom, right? This is a 3D shape. This is a real object. I could take the real 3D object on my desk and turn it upside down. I could knock it outside. I could tilt it against the wall so it's diagonal. You can rotate and draw a 3D shape in any direction. The base is the shape that's projected through space either to the same shape or to a single point. Now I notice in this that the front triangle gets projected back to another triangle. That's the shape that gets projected through. So this is not a rectangular prism. This is a triangular prism. And the big misconception is a base does not have to be on the bottom. The base can be anywhere on the 3D figure. It's just what shape is either projected through space without changing to its same copy on the other side, or what shape is connected to a single point. And that's like a dilation or a pyramid. All right, so this is find the number of faces, vertices, and edges. We didn't go over the Euler's formula, so I won't do it in this video. You can look that up. It's just a quick little this plus this equals this. So let's count. So on the first one, it says faces, edges, and vertices. So I'll count vertices first. For vertices, there are 4. For edges, there are 1, 2, 3. And then on the base, there are 1, 2, 3. So there's 3 on the base. Doesn't matter which base you talk about. And then there's 3 coming up from the base to the tip of the pyramid. So there's a total of 6 edges. Now just erasing that work really quick. If I want to count faces, I would go, well, there's 1 on the bottom, and then there's 2, 3, and 4 behind. So there's, again, 1 on the base and 3 coming up from there. So the faces, there are 4 total. And we don't need to go through, you can just count on those. But that's helpful in practicing just identifying the 3D shape and what is sticking towards me and backwards and what would this look like if I rotate it. So the next is, are these concave or convex? Well, again, it's just, is there an indent? So right here I can see these two go inwards. So this is concave. This other shape has lots of indents, right? Indent here. So this is also concave. This is, I can't quite tell what's happening here. If this is a hexagonal prism, or if this is sticking outwards even. But either way, I do not see any clear indents. It looks to be that everything is sticking outwards. So this appears to be convex. Now this says draw and describe the cross-section form. So this one, if I cut this appearing to be cylinder straight down, this would be a circle. Now if you cut it slanted though, as this width wouldn't change, but the length of this cut would get as long as we wanted, as long as we cut it, while the width would stay the same. This could become an ellipse if we slant it. But if you do it parallel to the base, it would be a circle. This one over here in 26, again, you're cutting it parallel to the base. So in 3D, it looks like this. But if we were to look bird's eye view down, like after we cut it and open it up, what we'd be looking at is either a square or a rectangle. Since it didn't label this picture, I'm just going to call it a rectangle. If you said square, that's okay. I would be very clear on this, whether we're talking about a square prism or, so on and so forth. In the next one, I've got a cone, and I cut through the tip straight down, and then this baseline is straight because it's flat on the ground. That's where my knife hits at the bottom. So this is just going to be a triangle. Misconception might be that instead of a triangle, you would get a circular round part. Now that's what the 3D object would look like. The 3D object would be like a wedge here. You would get part of the base, right? And it'd be 3D. But the actual 2D slice you'd be looking at is this. And then behind it would be sticking out that 3D wedge of it that you took off from right here. Okay, so just to erase that, you would just get that. All right, so what I'm going to do now is just do some super quick IXL. Should just take about, a few minutes. But hopefully you enjoyed the video, and good luck on your own. Okay, so what is the shape of this base? This one is a triangle projected through space. So although there are some sides that are some faces that are rectangles, The base that's projected through space is a triangle. It goes triangle at the bottom, stack of triangular post-it notes, to triangle at the top, so triangular base. What is the shape of its base? Well, since there's every single face is a triangle, this is a triangular pyramid. There's a triangle, whichever triangle you pick, doesn't matter. And then it connects to, so let's say we pick a side one. So here's our base, and then every single vertex is connected to this center. Vertex to point, vertex to point. So this is a triangular pyramid. The base of this is a cone. The base is the circle. The base of this is either a square or a rectangle, since there's only square as an option. Again, this is a base of a circle getting projected to a base of a circle. This would be a cylinder. This one has to be the square and then connected to a single point. If you try and say, well, like, why can't it be this triangle? Well, that triangle would be connected to 1, 2 points, so it would not be a pyramid. So this has to be that bottom and then connected to 1, 2, 3, 4. So single point to square bottom. Rectangle, because every face is a rectangle. So this is the bottom rectangle projected up, or the front rectangle projected back, or even this rectangle projected that way. So 3 different ways you could look at it, but all 3 bases would be rectangular. This one is a triangle projected through space. Again, you're like, well, why can't it be something else? Well, let's look. Okay, so if I try and say, all right, well, it's this face over here. It's maybe a rectangle. Well, let's see what that happens. From that base, there's 2 points you're connected to. It's not a prism, and it's not a pyramid. So instead, if we look at the base being a triangle and bottom, it is projected up to the same triangle. So there's a triangular prism. Every side is a triangle, so you can pick any one as the base and then say they're all connected to the other point, so triangle. Okay, and last one here, this would be a square base connected to a single point. So let's switch over to H2 now. Now H2 says polyhedron. No, it's got curves. Made a 3D dimensional figure out of clay. 5 vertices and 8 edges. Let's do some counting here. So this has no vertices, so it can't be that. This one has 8 vertices. There's 4 on top, 4 on bottom, so it can't be that one. The other one has 1, 2, 3, 4 vertices on bottom and a 5th on top. This one has 1, 2, 3 vertices on bottom and 1 on top, so 4, so it's not that one. Must be the second one. Okay, has a round shape like a ball. 8 vertices, so it can't be that one. This one we looked at last time had 3 on bottom and then a top, so that's 4. Can't be that one. That's not a polyhedron. It doesn't have any vertices. So we've got, it has to be this one. Though it is not a polyhedron, it's got some curves. Yes, that's made of all straight line segments. It's closed. A round base, so it has a base, which would imply it's a cone or a pyramid or a prism, essentially, but the curved version. So it would have to be this one over here. Is it a polyhedron? Yes, straight lines. It's closed. 4 vertices and 6 edges. So it can't be this one. So this is 1, 2, 3, 4 vertices. And there's 1, 2, 3 edges on bottom and 1, 2, 3 connecting up. That's 6 edges. 5 vertices and 8 edges. So let's see, this one right here would have 3 vertices on the front and 3 vertices on the back. That's 6 vertices, so it can't be that. Circle doesn't have any vertices. This one over here would have 4 vertices on top, 4 vertices on bottom. That's 8 vertices. It can't be that one, so it must be this one. All right, so the last IXL skill then is looking at cross sections. So here we go. Assume the objects are perpendicular, assume they're regular, all that. So cutting this cone right down the middle, we get a triangle. Cutting the ball through the middle, it looks to be flat, so perpendicular to that vertical diagonal, so we get circle. That would be, looks a little funky, but looks to be a triangle. That would be another one where we get a triangle. Rectangle. Rectangle. Let's see if it gets a little harder for us. Ooh, now we're cutting this like circular tube shape thing, so we get a little annulus. Circle. All right, it's not going to get much crazier, so that's going to be a rectangle. So we'll stop there. Hope you enjoyed the video, and good luck.